Okay, there we are. We should have audio now. Okay, perfect. Awesome, awesome. Well, we're back with Calculus Day 22, I think. Let's see. Okay, perfect. Okay. Wait, so it's confirmed we have audio. Okay, so I think we'll just go through and start with actually, I had like a pretty incredible like cognitive shift happen today with reading and learning generally. It was actually pretty profound, probably. I'd probably say like the top 10 concepts in terms of how they've affected me this year. Anyway, so this was from a video from the Stripe CEO, Patrick Collinson, and he talked about reading and how he favors a importance like based approach for reading and learning, where he views the world as having so much knowledge and so much potential learning, and that this potential learning and knowledge is really important to have, but that he doesn't yet have it. Okay, and then he ranks what he should read according to their importance, such that he's reading the most important thing that, he's reading what he believes to be the most important thing at the time, and it continues down the line of like this is, of utmost importance, which is like a really, really super powerful way to view things. And obviously it's like reasonable and coherent, but the power of this approach is that you're constantly ranking things that you are like potential things that you'll learn according to their importance. And then additionally, you have this sort of urge for learning based off like the huge amount of potential learning you can do. And the power of this approach is that, one, you are actively filtering things according to their importance rather than some, arbitrary sort of vague approach that people probably often use for selecting things to read. So you're ranking them according to importance. And then two, because you've identified it as the most important, you have way more motivation to do that thing, because like you've self-selected this thing as being the most important thing to read. And then also given the fact that you view the world as having immense amounts of knowledge and learning that is just like waiting for you, that like creates some sense of urgency or pressure to begin learning the thing. I just thought that was like really incredible. I think we often have pretty vague ways for selecting learning and selecting things like that. And it's definitely even a critique of this approach, right? Well, I guess I wouldn't say a critique entirely, but certainly this is like a more, I don't know, maybe classical approach, like topic-based approach. And this is good for, solidifying a foundation, but yeah, I think for, I guess there's two parts of learning, a more like, or you could have two areas of learning, a more like importance-based, like quick sort of, more important, well, Yeah, I guess I'll make the broad separation that we have a more sort of importance-based, just-in-time, like high-interest area for learning. And then we also have like a more structured, like focusing on foundations area for learning. So I think I'd like to sort of iterate on that and get a better idea of what I'm thinking there. But I think that is something profound. Anyway, so I think we'll just go right on in. I think I'm getting close to the point where I'll be able to burn through a few of these, or burn through these fairly quickly. And so that's quite exciting. So yeah, let's try to zoom through. Let's see. Okay, let's see. It has been a bit. Okay, slanted asymptotes. This is where the is the power of the maybe the power of the numerator is, or the highest degree of the numerator is 1 greater than, I'm pretty sure. Okay, I'm actually not sure. Check the degrees of the numerator and the denominator. If the degree of the numerator is exactly 1 higher than the degree of the denominator, perform polynomial long division. The quotient is the slant asymptote. Okay, so I was correct on the, actually I don't know if I verbalized that, but the numerator being exactly 1 degree higher than the denominator, but after that you're wanting to take the polynomial long division where the quotient is the slant asymptote. Okay. A conjugate. So I think I want to be more specific with this because I don't know if all instances of conjugate are this. So I believe it's the case that a conjugate is like x plus 1. The conjugate of it would be x minus 1. I'm not quite sure. That emerges from changing the signs of the operator. Oh, sorry, this is the form that emerges from changing the signs of the operators in expression. For example, the conjugate of a plus ba plus b is a minus ba minus b. It's often used to okay, yeah, that was the conjugate. Let me just double check that this is a general, like a general thing, or rather, like when. Or rather, I guess I'm saying if conjugate is used in differing ways. Okay. Okay, so the specific meaning depends heavily on the context. Okay. Maybe I'll need to specify that this is in merely algebra. Okay. Okay. How do you find the vertical asymptote? So you need to find instances where y is 0. Sorry, not y is 0. Where, y is undefined for a given x in a function. Typically, you reach a vertical asymptote approaching that particular undefined place or coming away from it. Yep. Okay, this is a conjugate in algebra. Horizontal asymptotes. Let's see. For rational functions. Okay, so I'd say when you're, well, when your degree is higher in the denominator. Okay. If the numerator is less than, okay, yes. Okay. Okay, so if the numerator's degree is less than denominator's, the asymptote is 0. If the degrees are equal, the numerator's degree exceeds the denominator's. There's no horizontal asymptote. Okay. Perfect. So, and we need to focus specifically on how I find it. So the operation will be check my numerator and see if the degree is less than denominators. If it is, the asymptote is y equals 0. If the degrees are equal, it's y equals leading coefficient of f over leading coefficient of g. Okay. Okay, a rational number is one that it can be expressed as a fraction of two integers. It can be infinite, but are repeating if they are. Whereas rational, non-repeating, non-terminating. Riemann sums is done, or calculating through Riemann sums is done through approximating area under the curve through like rectangles, and increasing the number of rectangles that you use to fit under the curve until you approximate the area under the curve. Okay, vertical asymptotes you find where it's for non-rational functions. Yeah, you just need to find areas where where you have like a discontinuity and where you approach infinity. Okay, undefined or discontinuous. Okay. Okay, yeah. I don't know that one yet. This means that as a function approaches positive infinity for its input, it never increases above a particular threshold. Oops. Okay. Okay, a vertical asymptote is because typically, or I guess it's often the case that vertical asymptotes appear in rational functions, and as the denominator approaches 0, or gets arbitrarily close, the output approaches infinity. This is the coefficient with the highest power, or the highest degree. Okay, inflection points on a function. This would be points in the, so we'll take the first degree derivative and then look for transitions points where we go from 0 to 1. Okay, why was I wrong? Okay, I think I'll Okay, so inflection points are where the rate of change is 0, because this would means that we're at a transition point for the first derivative. And the reason why my first inclination was false is because Okay, maybe oh, okay, okay. Okay. So I understand why I have this wrong. Because in this situation here, we're never we're never at a point if we take the tangent line where, okay, maybe in this instance here, but and some of these are bad tangent lines. Like we aren't hitting 0 at this point or at any point along this graph. Maybe you could say this here, but for the most part, if we look at something that looks like this, or even if I do slight, I am never changing from negative to positive. And so if it were like a pure sine wave like this, the inflection points would exactly match the where 0 is for would exactly match where 0 is for the first degree derivative, or I guess where the many zeros are, right? As each of these would be zeros. Okay, so being that that's the case, okay, so being that that's the case, we take the second order derivative because this determines the rate of change of our rate of change. Okay, so we find the where the second order derivative is equal to 0, and then we also find where it's undefined. Check the points around these values. If the inflection occurs, okay, so we'll send this one through, but I feel better at that, or better, I have a better feeling about that. Okay, so if the numerator is exactly 1 degree higher than the denominator, you take the polynomial division, or you take the quotient using polynomial division, and that is your vertical or your slanted asymptote. Okay, 1 higher, perform polynomial long division, the quotient, yep, perfect. Okay, bounded function, this is one in which as x approaches positive or negative infinity, we hit upper bounds in y. Okay, so it's described in terms of domains and I guess ranges as well, but aside from the terminology, that's correct. Horizontal asymptotes. Non-compute the limit if the limit is finite. Oh, okay, for non-rational. So we just oh yeah, of course. Okay, so we just compute the limit of as we approach infinity for x, and if our y approaches like a limit or like a number, then we do that. Okay, the derivative operator dx or d over dx. Okay, x and y is like integrals because we're measuring volume, and delta y and delta or over delta x is derivatives because we're measuring slope or rate of change. I don't know that one quite yet. Okay, a lower bound is that as x approaches negative infinity, we bottom out in the y, or in other words, our input domain is like all-encompassing, or sorry, but our range does not. Like there are values beyond which that never emerge. Okay. It means all inputs to the function, or the outputs for all inputs of the function, given equivalent inputs between the functions, the one of the functions for a given input is less than the other function. This is a expression with two terms. Okay. Rationalizing, this is where you usually divide, typically by using conjugates, I believe. Anyway, you're wanting to remove, it's an algebraic operation to make something easier to take the limit of. Multiplying by conjugate to eliminate square roots. Okay, so multiplying, okay, so not only is it rationalizing, okay, so the big idea is eliminating square roots typically. Let's see if I get this one correct, or if it's the same thing here. To eliminate radicals. Rationalizing is used to eliminate radicals, and typically involves okay. Okay, in calculus, how do you find horizontal asymptotes for rational functions? Okay, so we take the limit of the function, and if we're approaching a finite position y, well, actually, this is for rational. For non-rational functions, that is the approach we take, but there is a shortish hand version for doing rational functions, where I feel like this one was, if the highest degree is the same, you take the division of them. No, I think that was for slanted, though. Okay, no, that's correct. Okay, for rational functions, compare the degrees of the denominator and the numerator of the denominator. If the numerator's degree is less than the denominator's, the asymptote is y equals 0, which makes sense. Because if the degrees are equal, then y is the leading coefficient of f over the leading coefficient of g. Okay, we'll go through that one again. Polynomial is it's a term having a, it is an expression having, more than one term. Or one or more terms. Oh, I guess, yeah, it would include one. Okay, so we'll send that through again. Okay, so for a function to be continuous at a point, you could take the limit. You can take, or the point exists, one input. You can take the limit of the point, and the limit of the point, and the point, taking the limit of the point, and just taking the point given the function are equal. It's like 2.7 something. And it is used for description in growth and decay in nature. Constant, yep. Okay, it serves as a natural base for logarithms. Actually, I'd like to, yeah, I think that's good for now. I just jump discontinuities where a number is like pretty much skipped, and it cannot be removed. Okay, the squeeze theorem states that for functions that are sort of like, so a function A is less than or equal to function B is less than or equal to function C, and A and C's limits are the same, then we know that B's limits are the same as well. Okay, if near a point, let's see. Yep, okay, yep, that's correct. Okay, so in the context of the integral symbol, which is the elongated S, or no. No. That's well, I guess we're not talking about the integral. Oh, I guess in the context of the... typically it's a lim and then an arrow to the limit. Oh, lower and upper limits. Oh, okay. For a given... Okay, that makes sense, right? Because for an integrals, we're taking area under the curve, and we'd have limits in place. Okay. I think I was, yeah, I guess confusing limits as we take them, typically for a function and in the context of integrals. So, okay. Okay, so it's used when a function is difficult to evaluate directly. Right hand and left hand limits. Right hand is like as we come from the like positive infinity to this point. Left hand is when we come from negative infinity to this point. Or I guess from like the negative side. A radical is something that has a square root. Yeah, is a mathematical expression involving a root. Okay. Actually, I'd like to ensure that I have mathematical expression there. Discontinuity is non-removable when you can't make an algebraically equivalent function that removes the discontinuity. Okay, you find inflection points by taking the second degree derivative, finding where it evaluates to 0 undefined, and then determine, given those points, if you okay, determine if like before and after those points we're going from like negative to positive, or if it's always 0, right? Yep, okay, perfect. Okay, that's good. Okay, the mean value theorem states that for like a given secant line on a closed loop from a point A to point B, that there is a given tangent line that is parallel to the secant line, given that we could integrate on an open interval and that the function is continuous on a closed interval. Continuous on a closed interval, differentiable on an open interval. Yep. Okay, perfect. Okay, composite function in calculus is one in which you have like a function inside a function, or a function composed of many functions. One or more functions. For horizontal asymptotes for non-rational functions, you take the limit of infinity, and if it approaches a finite value, you have the asymptote. Or if the output approaches a finite value. Okay, rationalizing is done typically when you have a radical within when you have a radical, and then you multiply the radical by, I believe it's conjugate, to be able to work with it easier. Eliminate radicals typically involves multiplying by a conjugate. Okay. That's good enough for now. This is an expression with one or more terms. For rational functions, finding horizontal asymptotes, if the degrees are the same between the numerator and the denominator, you take the leading coefficient of the numerator and divide by the denominator. If the numerator is one less, or sorry, if the numerator is less than the denominator, then the asymptote is 0, y equals 0. Perfect. Radical is an expression that involves or includes a root. Upper limit is on the top of the S, lower limit's at the bottom of the S. A squeeze theorem is used when the function is difficult to evaluate at present. Is when the visual yeah. So what do we mean by the function is difficult to evaluate directly? What are we doing when we're evaluating here? Particularly around a point of interest. Okay. What? In what situations is a function Okay, so I guess it just makes it easier in particular situations. Oh, interesting. Oscillating functions are difficult because x approaches 0 infinitely many times. Okay, that's pretty good. Okay. Okay, I do have an issue with like how things are going right now. Because like I'm needing to wrap up here soon, and I haven't done anything new. And so I think I might extend these sessions to be 2 hours for now, just so I can get through calculus. Because right now I'm just really not making much progress in the time that I have. Yeah, let's see. Yeah, I think maybe if I make them an hour and a half, I don't even know if that's enough though. Okay. Okay, so I'll do an hour and a half tomorrow, and then I think I'm going to do like a multiple hour one on Friday to see if I can just finish it. Because, yeah, I mean, like it's great to be able to like continue to go over stuff to have a better understanding and dive more into it. But also I'm like not making any progress more on like the stuff I'm learning or on calculus. Like we're like often we don't make much progress on the test at all. So, okay. Okay. I think that's reasonable. We'll probably just do that. So let's try 2 hours tomorrow. See how that goes. And then, yeah, we'll try 2 hours tomorrow, and then we'll shoot for Friday as well. Because I'd like to like push through this and start on statistics. Okay. Okay, perfect. I think that is good. And I think I'm going to shoot for like, I don't know, 4 hours on Friday, 3 hours on Friday. Anyway. Okay, sweet. I think that is everything for today. I'll see you guys tomorrow.